All right, I'm still getting used to things here this morning. Hey, good morning, BC Calculus students. My name is Mrs. Charnley. You may have seen me in the hallways around a little bit in Easton. This year I am remote teaching, and Mrs. Oakes is teaching the hybrid students, but we've decided to work together and combine resources, so here we are. I will make some of the videos for the BC students. Mrs. Oakes is there to answer all your questions. I'm there to answer all the questions for the remote students. So we will figure all of this out together. So this morning I am working on my back deck, and it's sunny and beautiful out. And we're going to talk a little bit about limits, rates of change in tangent lines. So we're really jumping into calculus. What is calculus? Calculus is all about rate of change. How does one change affect another change? And it's really, really awesome. I know I only teach high school calculus, but calculus is used to model things that you can't see or you can't touch. So things that are really, really big, you're going out into space, things that are really small, blood vessels, the way that things move through our body, and anything and everything in between. I couldn't even list all the examples. It's used a lot in forecasting weather. I don't have the background to do that, but I can help you with the beginning calculus. I know some of you are headed off to be scientists and engineers and mathematicians. You will definitely need calculus for all of those things. So, rate of change. Our objective today is to introduce the concept of a limit and how limits arise in the study of rate of change in tangent lines. Excuse me, so warm up. If I travel 200 miles and it takes me 4 hours, what conclusion can be made about my speed? Well, 200 miles, 4 hours, this is like an Algebra 1 problem, so think about it for a second. How fast are you going? Well, you can say that you're going 50 miles an hour. Well, how did you get that? We said that 200 divided by 4 is going to get you 50 miles per hour. Excuse me, still early. That's great and wonderful and all, but I used to give the example. I graduated from Lafayette, and my parents' house was exactly 100 miles. We measured it once on the car. It's exactly 100 miles north, and I can make that trip in 2 hours. So my average, just like this problem, my average rate of speed was 50 miles an hour. But then I'd ask students, well, can you go 50 miles an hour if you're driving on 33? You've driven on 33, you've ridden on 33. Not the lower half, no. You got to go 65 or you're going to get run over by a truck. So 50 is too slow for that part. But by the time you get up to where my family lives, there are dirt roads and back roads. And if you go 50 miles an hour, you'll pop a tire. Been there, done that. So you want to keep it slower. So that 50 miles an hour is not your speed for the entire trip, but it's your average speed. So sometimes you're going faster, sometimes you were going slower. So we want to look at what's that instantaneous piece right in the middle. That's the good stuff. So what we're going to do is look at velocity. Do you remember these from Algebra 1? Recall from Algebra 1, rate times time equals distance. Hold please here, I'm a little rusty. Here you go, rate times time equals distance. You did all those train problems and the bus problems, rate times time equals distance. Now we're gonna make that a little bit more sophisticated, and we say that velocity times time is equal to the change in position. You wanna consider an object moving in a straight line. You want linear motion. We're not talking about some of those arcs that you'll get into in physics. We're keeping everything in a straight line. So straight horizontal, straight vertical are really our two situations that we're looking at. Now your average velocity, hold please, is going to be pause this. All right, we're back. Had to double check something. It happens. So we are chatting about our velocity times time is the change in position. So how can I rewrite this? I lost my pen. How can I rewrite this to calculate the velocity? Well, we would divide both sides by the time. So our velocity, I'm going to write that down here in this box, your average velocity is going to be the change in position over the change in time. The change in position over the change in time. Now, that's terrible notation. We want to do that a little bit better. So we use delta S over delta T. Now, delta means change. You may have seen that in your science classes. Delta means change. You see a change in temperature or change in different things. So delta means change. We use S for position. I believe if you're taking your physics class, I don't think you use S for position. I think you use a different letter. But in calculus, we use S for position. And T, lowercase t, is time. So if we use some of our wonderful function notation, this becomes S of T1 minus S of T0 over T1 minus T0. T0 is your initial amount. I hope that's familiar to you. Maybe it's not. And T1 is your final amount. So T sub 0, your initial time. T sub 1 is your final time. Now, does this look familiar to you at all? I mean, does this look like something you've seen before? You subtract one value over another value subtracted? Think about it for a second. It should, because it's really just this guy. Do you remember this? Y2 minus Y1 over X2 minus X1. The green doesn't show up very well. That's just the slope formula. How long have you known about the slope formula? Algebra 1 at least, maybe before Algebra 1, maybe in pre-algebra, but your slope formula, Y2 minus Y1 over X2 minus X1. Slope is a rate of change. When we talk about slope up until this point, we've always been discussing the slope of a straight line. Now we're going to make it a little bit more sophisticated. We're going to start to talk about the slope along curved lines. So that's where the calculus is really, really powerful. But we're really just talking about slope. So a couple things that I need you to know about instantaneous velocity. It tells us speed and direction at a particular moment. This moment cannot be represented as a ratio because then you'd be divided by 0. So at a particular moment, that difference between time 0 and time 1, we're looking at no time at all. So we can't divide by 0, that doesn't work. And we use it to estimate the average velocity, or we estimate the instantaneous velocity by taking average velocity over successively small intervals. So very, very small pieces indeed. So I'm going to read those again instead of writing them out. So instantaneous velocity, 3 bullet points. I want your notes right here. Tells us speed and direction at a particular moment. Cannot be represented as a ratio because then you would be dividing by 0. And we estimate the instantaneous velocity by taking the average velocity over successively smaller intervals. So we want those intervals to get smaller and smaller and smaller. So if I want to know my instantaneous velocity as I'm driving up to my parents' house, I don't look at that entire 2-hour window. I look at a 5-minute window, and then I look at a 2-minute window, and then I look at a 1-minute window, and maybe I look at a 30-second window. So that 2 hours is too big. So you want it to get smaller and smaller and smaller and smaller. So what does this look like? What are we going to do? We are going to actually try this out. Galileo found that the distance traveled by a falling object can be represented by the formula S of t equals 16 t squared feet, assuming no wind resistance exists. So you're going to talk about that friction due to wind in your physics class. We don't have to worry about that with this equation. So 16 t squared feet. If we have an object falling due to gravity, it travels 16 t squared feet. So example 1. The stone is released from the top of a building and falls to the ground. Find the average velocity from 0.5 seconds to 0.6 seconds. And can you find the instantaneous velocity at 0.5 seconds? So my notes should have a little 0.5. Okay, so for part A, average velocity. Average velocity, average rate of change. Remember, you're just talking about your slope formula. average velocity. So that formula we used above is the position at time 1 minus the position at time 0 over time 1 minus time 0. T sub 1 minus T sub 0, S of T sub 1 minus S of T sub 0 over T1 minus T0. So now we have to put in those values. So for us, just because we're a little rusty on function notation, I'm going to put it all in. That second time is 0.6 minus the initial time is 0.5 seconds. So we're talking about 1/10 of a second. This is a tiny interval over 0.6 minus 0.5. Now, I have to stress, because when you go to do practice problems, this 16t squared is not any average velocity. It's only for a falling object. I have students try to use it everywhere. It's only for a falling object. Are you allowed to use this formula? So the 0.6 goes into that 16t squared. So we have 16 times 0.6 squared minus 16 times 0.5 squared over 0.6 minus 0.5. Now, what you need to do is grab your calculator, put those in, use parentheses appropriately, use exponents appropriately, and find out what your average velocity is. And I'm going to do the same because I forgot to bring my calculator with me. So I'm going to pause this again. I'll be right back. All right, we're back again. Oh, please, where's my screen? No? All right, there we go, I'm back. I have my trusty TI-84 calculator. I hope you have your trusty TI-83, 84, 89 if you're that lucky, but 84, 84 plus is probably the way to go. If you don't at this point, you can use anything that you have to calculate, apps on your iPad or what have you, but by the time we get to the AP exam, you can't use your iPad. You gotta have a calculator. So when I put all these in my calculator in little steps, I wind up with 17.6. So 17.6 what? Well, we measure the top in feet. We measure the bottom in seconds. So 17.6 feet per second is my average velocity between 5/10 and 6/10 of a second. Well, that's great. That's a pretty small interval. However, it still doesn't tell me exactly how fast I'm going at 0.5 seconds. And that's what part B is all about. So what we need to do for part B is the same thing that we did in part A, but over smaller and smaller intervals. So for part B, you have to decide the intervals. I didn't tell you what they were. You have to pick them. So we can't remember what I've used in years past, but maybe we'll use 0.4 to 0.5. Give my stylus here. And then a smaller interval, 0.45 to 0.5. And then we'll use 0.49 to 0.5. And then we'll do it again. This time on the right-hand side, I'm going to use 0.5 to 0.51. And we'll use 0.5 to 0.55. How do I want to do that? I want them symmetric. Yep, that's right. And then we'll use 0.5 to 0.6. So these are time intervals. These are seconds that I'm picking these decimal values between. And what I've done is I've chosen small, close intervals, each to 0.5. And so what we're looking to do is find a pattern. That's really our goal here, is to find a pattern. So what we're going to do is this problem that we did for part A once. We're going to go through and do it 6 times on the right-hand side. I know that feels like a lot. And if we were in class, we would divide up the work a little bit, but we are not. So Pause the video here. Take your calculator, take a second, go through and figure out what all of those increments are, and I'm going to do the same thing. All right, we're back. So I've used my calculator. I've gone through to calculate all of those decimals. If you're not getting those decimals with your calculator, excuse me, I would like you to go through and try again. Check your parentheses, check your decimals. Maybe you need to do it in smaller bits instead of the whole thing. A lot of times students will try to take this part, the numerator, and not use parentheses around that. You technically need grouping symbols all over the place. So if you're going to do this in your calculator all at once, you need grouping symbols up here in the numerator, then your divide, and then grouping symbols in your denominator. Or some of you I know go through one step at a time. Either way is fine. Just make sure that you're getting these decimals. Now, what we're looking for is a pattern. What's going on here? What do you see? So randomly, if you look at one interval, it looks like 14.4 or 16.6 or that 17.6. I guess I just redid a value we already had, right? That's 17.6. So I want to know the instantaneous velocity at 0.5 seconds. Do you see a pattern? Do you see anything happening? If I go from 14.4 up here to 15.84, these are getting bigger, but they're not getting bigger than a certain value. If I look at the right-hand values, that 17.6 to 16.8 to 16.16, we're getting smaller. So the question is, what happens right here in between? What happens if I made that interval as small as possible? If I could go from 0.5 seconds to 0.5 seconds without dividing by 0, what would this missing number be? So when you look at that, I hope there's a number that's sticking out at you. It's actually 16. And we're talking about 16 feet per second. That is the instantaneous velocity at 0.5 seconds. So the question I always get is, because we don't like to do extra work, Mrs. Charnley, how come we can't just choose a really small interval? How come we can't do 0.4999 to 0.5? Well, you can use that as one of your intervals, but that doesn't help you figure out the pattern. You have to have enough data for a pattern. So I like to tell my students 3 points on the left and 3 points on the right, or 3 intervals on the left and 3 on the right. Kind of gives you enough of everything. But you gotta have enough to see a pattern. Bare minimum, you would need 2, but 3 data points on each side is nice. So average rate of change, here's the big thing for today. Average rate of change, 2 points, 1 answer. Instantaneous rate of change right now, you need multiple intervals, and you're looking for the pattern. You want to see the pattern, not just one value, but you want to see the pattern between the values. And as a reminder, that 16t squared is only for a falling object. All right, let's see what we got next. Tangent line. Here we go. You remember these things? The average velocity is the slope of the secant line. Remember we said we're talking about slope today. So you can think of that. Let's fill this in a little bit. The slope that your secant line is your change in y over your change in x, which is y2 minus y1 over x2 minus x1. That's good old algebra 1 notation. Again, if we want to make this a little bit more sophisticated, in our function notation that we're dealing with, it's the position at time 1 minus the position at time 0 over time 1 minus time 0. It's really the same thing. It's the same thing. So don't get nervous about the function notation. And I'm using s instead of f. It's the same thing. Now, here's the cool thing. As the time intervals shrink to 0, as we're looking at a smaller and smaller time interval, the average velocity starts to approach the instantaneous velocity. So the slope of the secant line approaches the slope of the tangent line. So right here in this first picture, the average velocity is equal to the slope of the secant line. So the secant line, as a reminder, touches your curve in 2 points. Maybe you remember that word from geometry. So here's your delta s over your delta t. I guess I can add that to our notation up here. Delta s over delta t equals, I gotta get a better stylus, is equal to the position over the time. So we have the average velocity is equal to the slope of the secant line. Well, what happens as this point right here starts to get closer to this point? And that's what's going on in the picture on the right. Your point on the right is getting closer and closer and closer. So if you watch this blue line, I don't love this picture. That's what's going on in a different graph. Let's come back to this one. If I look at my secant line, as a reminder, a tangent line only touches in one place. So there's my tangent line. So if this point gets closer and closer, there's my next closer point. That's still a secant line. Still a secant line, but the slope of that secant line is getting closer to the slope of the tangent line, and that's the idea. And that's what they're trying to show in the right-hand picture. That this secant line, this black line, goes through those blue lines, and then it starts to approach the tangent line. So the smaller that interval gets, the closer you are to the instantaneous velocity. So a little YouTube video there for you to watch about instantaneous velocity. Take a second and find that if you can. Pause your video here. So what is that instantaneous velocity? Well, the instantaneous velocity is the slope of the tangent line, and I think I ruined that already. I told you in the step up above. It's the slope of the tangent line. So average velocity, slope of the secant line. Instantaneous velocity is the slope of the tangent line. So example 2, using example 1, find an approximate value for the instantaneous velocity using the tangent line. So what we're going to do, well, what is 16t squared? So S of t equals 16t squared. That was the equation given in example 1. We want to find an approximate value for the instantaneous velocity using the tangent line. All right, so we are going to use example 1 to find the approximate value for the instantaneous velocity using the tangent line. So we know the instantaneous velocity is the slope of the tangent line. So what we have in that first one is S of t equals 16t squared. If we just turn that into function notation that we are used to, we have y equals 16x squared, which would be how we would graph it. So what I've done is I've hopped over to Desmos and I've graphed this for us. I have the parabola, I have the tangent line, I've put them in already. I've chosen 2 points. I've chosen the y-intercept of my tangent line, which is 0, -4. And I've also chosen that point where we're tangent, the x value of 0.5 and that y value of 4. So what we could do is we could actually go through and calculate the slope. So I know I have the point 0, -4. I have this point 0.5 and 4. I'm gonna hop back over to our notes. By the way, Desmos is very awesome. I just kind of pinched it to expand it so that I can see what was going on. And you can just touch those important points and they will label them for you. I guess if you touch them twice. So things like that are kind of handy. So you do have Desmos available and self-service. And I'm using Notability to write up my notes. It's not in self-service for you guys because it's a paid app, but if you happen to have your own device and wanted to download that one, I think it's $9. It's a little pricey, but it really helps with the stuff. So what points are we talking about? We are, from the other page, we had 0, -4, and we had 0.54. So when we go to find our slope, y2 minus y1 over x2 minus x1. So I'm going to say 4 minus a -4 over 0.5 minus 0. So the numerator is 8, the denominator is 0.5. Divide those out. It feels like it should be 4, but it's not. It's 16. The slope of that tangent line is 16, and because we're talking about feet per second, it's 16 feet per second. But that's what we got from all that calculator work, making all of those different quotients ourselves and finding that pattern. We also got 16, so it does work. All right, here we go, example 3. Assume that the period in seconds, that's a capital T, of a pendulum, the time required for a complete back and forth cycle is 3/2 root L, where L is the pendulum's length in meters. Find the average rate of change for 1 to 3 meters, and then find the instantaneous rate of change when L is equal to 0.3. So this is the same idea as the Galileo problem. However, we have a different equation. So I don't want to see 16 in this one anywhere. So for that first example, part A, we are going to say, instead of position, it's that second value. So I'm just going to jump right in. We're going to say rate of change is equal to 3/2 root 3 minus 3/2 root 1 all over 3 minus 1. So this is in lieu of, or a different equation, a different function than that 16t squared. So use your calculator, use parentheses, square roots appropriately, all that good stuff. I'm going to do the same thing, 3/2 times square root of 3 minus 3/2. All this is divided by 2, and I get 0.549. Where the top is in seconds, this feels upside down, and the bottom is in meters. That is correct in this case. Now, to find the instantaneous rate of change when L equals 3 meters, that same idea, you want to choose your own intervals. Probably want to use some smaller ones. So if we did 2.8 to 3, 2.9 to 3, and maybe 2.99 to 3. And then again, I like it if you check the other side as well. So I like to be symmetric when I do these, 3 to 3.01, 3 to 3.1, and 3 to 3.2. So same idea, I want you to take those different values, put them into this formula that we just used over here. This one. But now you're replacing the 3 and you're replacing the 1. Anytime you see the 3 and the 1, those are what you're replacing. So pause your video right now, give yourself a couple minutes, go through and calculate those different differences. I'll do the same thing and then we'll meet back here and compare. All right, we're back. So I've used my calculator. I went through to calculate all those differences. I kept 4 decimal places. I should have told you before you left. The more decimal places, the better for some of these. You could go 5, 6, 7 and go crazy, but 4 is pretty good to see a pattern. Clearly, all of these start with a 0.4, and then they start to kind of get close to a value. This is the region that we're looking. This is where that 3 would be. The instantaneous velocity of 3. Whoops. We don't need that, do we? You guys are better with split screen than I am, and I just accidentally did that. We're back. Always something. Always something. All right. There we go. So those are the values that I have. So I really want to look for a pattern. I want to see what's that instantaneous rate of change. And I'm going to write that down here. My rate of change, instantaneous. I'm going to go with 0.4. Clearly there's a 3. Now I've got 2, 7, and 3, 4. I'm kind of guessing at this one. I'm going to go 3, 0. Something that's exactly in between there. And I left my units off, but again, these are seconds per meter. That determines the period based on the length that we're we're going on. So our instantaneous rate of change for that pendulum. Now, other rates of change, so we kind of already did this, applies to any function y equals f of x. So that's what we just showed you with the pendulum. It doesn't have to be a following object. So it's delta f over delta x, kind of like your slope formula. So you can say f at whatever that second value is. If it's time, great. If it's something else like feet, that's okay too. Maybe it looks something like this. But again, it doesn't have to be. Well, no, I just did that wrong. What did I do wrong? I used t's. What's that independent variable on the bottom? That's an x. All right, let's try again. F of x1 minus f of x0, this looks better, over x1 minus x0. There you go, your average rate of change. So your independent value is that x, that second value for the independent value over the initial value. So there you go. All right. Now, I have a practice worksheet for you to try. Do your best. It's a PDF. You can mark it up. Everybody's trying to go as paperless as possible. If you get home and you're better off printing it out, that's fine. If you want to work on lined paper, that's fine too. And just use the worksheet as a reference. So do your best with these. Reach out to myself or Mrs. Oakes if you have any questions. We are here to help you out. This is a crazy, crazy school year. We're going to do our best to teach you some calculus and get you ready for that AP exam. So average rate of change, instantaneous rate of change. We're just talking about slope. I'll see you guys.